Welcome to our session on evaluating the outcomes of artificial intelligence models. Today we are looking at how an auditor ensures an intelligent system is actually doing what it was built to do. Let us talk about the real-world utility of this knowledge. As an auditor, you will rarely write the underlying mathematical code for these advanced systems. Instead, you will use this framework to examine the testing results of an artificial intelligence tool and definitively tell your organization if it is safe to deploy. You will act as the vital safeguard that prevents a business from relying on software that makes terrible or secretly biased decisions behind the scenes. Our first major concept is the testing of model outcomes and managing false positives. In simple terms, a false positive is an alarm that rings when there is absolutely no danger. Imagine a home security system that automatically calls the police every single time the family dog walks through the living room. In the realm of auditing, you are not expected to sit down and mathematically calculate the exact frequency of these errors. Instead, your job is to review the formal testing logs to see if the engineering team documented and addressed them. You will ask tough questions about the quality and the variety of the historical information used to teach the system, as bad training data is usually the root cause of these false alarms. This leads us perfectly into the concept of underfitting. Underfitting happens when the software model is simply too basic to understand the complex patterns hidden within the information it is given. To explain this without the jargon, think about trying to predict the entire global climate for the next decade by only looking at the weather outside your kitchen window for 5 minutes. You simply do not have enough perspective or detail to see the big picture. In technical terms, the model performs terribly on the training data, which acts as the practice test, and it also fails miserably on the testing data, which acts as the final exam. When an underfitted model is forced into the real world to make a prediction, it will often be wildly inaccurate and heavily biased. As an auditor, you must verify that the engineering team has a clear investigative process to figure out why this failure occurred. You must ask if the raw data itself is flawed, or if there is simply not enough data available. You also must ask if the mathematical structure is entirely wrong for the task, perhaps possessing too few parameters, which are the adjustable internal dials the system uses to learn, to capture the required level of detail. On the completely opposite end of the spectrum is overfitting. Overfitting occurs when the system learns the practice information too perfectly. It essentially memorizes the training material completely, absorbing all the random errors, background noise, and weird mistakes along with the facts. Imagine a student who memorizes a practice exam line by line, achieving a perfect score. But on the day of the real exam, the teacher changes a few names and numbers, and the student completely fails because they did not understand the underlying concepts. They only memorized the exact phrasing. An overfitted model looks like a massive success during early development because it scores flawlessly on its practice runs. However, the moment it is released into the real world and sees completely new, non-test information, it crashes and burns. Just like with underfitting, you must validate that the developers are actively running analyses comparing practice results against testing results to spot this trap. Deploying an overfit model is dangerous because it will generate faulty, unpredictable outputs when faced with real-world scenarios. Next, we need to discuss outliers. An outlier is a piece of information that is completely abnormal compared to the rest of the group. It represents a drastic skew from the normal distribution, showing up as an abnormally large or small value. Think about tracking the height of adult humans, and suddenly your medical records show someone who is 50 feet tall. That 50-foot measurement is an outlier, likely caused by a broken sensor or a simple typo. If you feed this crazy data into an intelligent system during its learning phase, the system treats it as reality, which introduces immediate failures into the training process. Outliers are not harmless background noise that can just be ignored. Your role is to confirm that the team uses specific software tools to hunt down and test for these abnormal numbers at every single stage, from initial data gathering all the way through to final validation. If the engineering team decides to keep an outlier in the system intentionally, you must verify that they did so by design and documented a valid business reason. A great practical technique for auditors is to take a random sample of the raw training data and load it into a visual spreadsheet or a dedicated graphing dashboard. By looking at the visual distribution yourself, you can easily spot these bizarre numerical spikes before they ruin the entire project. Finally, let us address the impact these technologies have on reducing our own workforce needs. Automated calculation tools are already taking over repetitive accounting tasks in the financial sector. This practice will absolutely increase as new, more sophisticated products enter the corporate marketplace. However, the constant industry hype that artificial intelligence will entirely replace human auditors is deeply exaggerated. Think of it like buying an industrial dishwasher for a busy restaurant. The machine scrubs hundreds of plates incredibly fast, bringing massive efficiency to the kitchen. But you still need a human health inspector to verify that the water is hot enough, the soap is dispensing, and the plates are actually clean. Intelligent software gives us opportunities to achieve more precise, efficient, and accelerated results. But human professionals are strictly required to validate that the machine is working correctly and that the foundational data underlying its output is accurate. To quickly recap what we have covered today, we explored how reviewing testing outcomes is vital for catching false alarms. We defined underfitting as a model that is too simplistic to learn the data, and overfitting as a model that memorizes practice data but fails when exposed to real-world scenarios. We discussed the critical danger of outliers, why they must be investigated, and how auditors can visually spot them. And we clarified that while automation brings incredible efficiency to our profession, human oversight remains irreplaceable. All the important topics and concepts from this session are covered in the multiple choice questions on RooCloud.com. You should ideally solve the chapter questions to reinforce your learning before moving on to the next session. Good luck with your continued studies, and I will see you in the next episode.